Maya or Houdini or other software. So you've already seen my background. We can skip that. This is the background of the other presenter who originally gave this talk. Davide has worked on plenty of movies, as you can see, from the 300 to Happy Feet. And now he's at Pixar as a colleague. All right, so this is where the presentation takes a turn for the geek in a big way, because I'm going to tell you guys how a renderer works, or how the various ways renderers can work. And in particular, I'm going to talk about two ways to render images: rays and ray tracing. I'm going to talk about them in the context of RenderMan. And the reason, again, I'm talking about RenderMan is because still it's the dominant player in the industry, and also, because of all those benefits I mentioned before. And again, RenderMan is not just a PR man; it could be an interface that many renderers use, like a 3Delight, the free one I mentioned, that I recommend you guys give a try. So now I'm going to explain the difference between rays and ray tracing rendering. So rays is and this is a little image that shows that. So RenderMan does both rays and ray tracing rendering. It started off with rays. Now it's a pun actually. Rays is an acronym for render everything you ever saw. We love acronyms in the industry. However, it's also a pun. If any of you are familiar with the geography of Northern California, there's a lovely area called Point Reyes, and this is actually the road to Point Reyes. That was an early computer graphics render, and so the name of the rendering algorithm was based off the scene they used, which is Point Reyes, but it's also a render everything you ever saw. It also means kings in Spanish. But anyway, so that's the first algorithm I'll talk about. And it goes back to the 80s. So it's designed to work on very weak hardware. And there's a number of terms that come up when it comes time to tune the parameters of a rays renderer. And what I'm going to hope to do is sort of explain what these things mean and why they're there. Now, there's a reason it's been successful. It's just because it's so efficient, especially at smooth surfaces, motion blur, and depth of fields. And in particular, what you can compare it to is ray tracing. Rays, pretty much overall, is a faster way to render ray tracing, mostly because it segments the scene into small buckets that it can render independently of every other bucket. So there's always a divide and conquer approach to render a scene, no matter how large it is. And in fact, this is the basis for modern OpenGL and graphics card rendering. So, for instance, in the viewport of Maya, you don't wait for your render. You just see your geometry. It's really fast. And that's done through the graphics card of your computer. Your AMD or your NVIDIA card. And what really is going on underneath the hood is there's a simple version of rays rendering that is running on your graphics card that is creating it on the fly. What rays in RenderMan is essentially a higher quality version of that for film rendering. And this is the basis, again, for OpenGL, but also for a lot of film stuff. And there's two main ways that the renderer, there's two main stages in the rendering. One is this sort of global stage, where it figures out how to segment the scene into small areas that are kind of independent of one another. And then once you're in that area, you can do higher level shading and refinement of it. So we're going to start with the left side, then we're going to move to the right side. So in the global sense, we start again, I mentioned this a couple times, RIB. This is the file format that you pass to the render farm that it renders. It's everything you need to know to render a single frame. You can almost think of it like an HTML file. That's everything the browser needs to know to render your web page. RIB is kind of like HTML, but for rendering. is not a program, you know, just the same way that HTML is not a program. It's a description of what's there, what the layout should be, where the details are. Bound is the next stage. When you're doing the raise render, you only care about what's in camera. Now this is very different from ray tracing, because you think, well, what if something is casting a shadow and is off screen or being reflected? Raise has trouble with that. That actually requires you to render multiple passes, which is compatible, but it also is what allows it to be fast. Each pass is going to be very fast. Because we basically, everything that's out of the camera, we throw it away. We don't have to worry about it. That is different from ray tracing. Same thing is, so once you've done that, once you throw away everything that's outside of the camera, that's not visible on the screen, you divide the image into a bunch of sections called buckets. And yeah, basically, you just split it up. And the smaller the bucket, the slower the render, but the less memory it uses. So more buckets means you could render more at less memory. So if you ever run out of memory, you can reduce your bucket size. Next, you split your geometry into what's called primitives. Primitives you can think of as the highest level description, like say a face on a polygon, a patch for nerves, or if your primitive is a teapot, the entire teapot. But it's like, you know, the coarsest description. Once you split it up, I don't know, we call them patches now. We divide those into a bunch of patches, and we sort them front to back. This is sort of what we do as the first stage. Get rid of everything off camera, turn it into a bunch of primitives and patches in a bunch of buckets. All of these can be rendered independent of each other. So think about it. Let's say you have a render farm or many threads in your machine. That means each thread or each machine can work on one bucket and not have to care about what's on the other machine. So this is an easy way to parallelize render too. That's actually why a graphics card is so fast with OpenGL. It's essentially a little supercomputer that just does this. On your machine, splits it up and pushes it through the parallel. Now, once you're done with that, now it comes time to do dicing. Dicing means we divide the geometry into 1 micropolygon per pixel, roughly. And so it doesn't matter if you start with NURBS, start with subdivisions, a curve, polygons, you always get 1 micropolygon per pixel. And this is what allows you to do things like change what the surface looks like at render time. You can move these micropolygons around, and they actually are all connected to each other continuously. So that's sort of what allows us to do that displacement trick I showed you guys earlier. In the OpenGL analogy, if you ever heard of a fragment, that's what these are called in OpenGL. The term shading rate refers to how many micropolygons we have. So bigger shading rate means bigger micropolygons. Bigger micropolygons means less quality but a faster render. So shading rate is the main quality amount we have in render map. It controls how fine we see these dice, and as a result how many points we shaded. And once you dice them, we combine them together into things called grids, and we'll talk about that a little later, but a grid allows us to actually shade a bunch of points at once. There's another way we can have parallelism in a render. So once we have it diced, 1 micropolygon, the other thing like I should mention about dicing is because we're dicing 1 micropolygon per pixel, if you have a surface like a NURBS or subdivision that's smooth everywhere, you never see a faceted edge or straight line. You don't have to change something like tessellation rate, as you sometimes do. It's always smooth at any detail, because it always gives you 1 micropolygon per pixel. You'll never see a hard edge if you don't want to. Sometimes you may want it, like if you're shading like a gemstone or something. But that is one advantage you have of this sort of on-demand tessellation, is you never need to see a faceted edge. The next stage is shading. And shading is a term we use all the time in computer graphics. You might think of shading as a process of making materials or a color on your object. But in terms of what a renderer does, a shader is a small program that takes one of these micropolygons and uses it to compute where the micropolygon is. You know, you can move it around, that's displacement, You can figure out what opacity is, and you can tell its color. You have position, opacity, color, which you also say normal. That's what a shader does. Program takes in a micropolygon, can do whatever, and then sets P, C, O, and N. And it also can set other variables. We call them AOVs. That's useful if when you render, you want to have many images at once. Maybe some for depth, maybe some for, some for position, if you want to do 5, or even an ID could be something a shader sets. If you want to hold out maps, you can pause it. All right, so once we do that, only after we've shaded the points, we can then start forgetting about stuff, because once displacement is run, we can tell if a micropolygon will never be seen, if it's covered by other micropolygons. So we can do visibility testing here. So there's a common expression in the industry: the fastest code is the code that never runs. That's what this does with visibility testing. We check if there's any micropolygons that are absolutely not to be seen. We get rid of them. That process, so then once we've done that, we have a bunch of shaded micropolygons. Then we can start sampling them to figure out what the final color of the pixel is. And this is where the anti-aliasing kind of happens, at least in image space, as well as things like depth of field and motion blur. Seems a little esoteric, like, all right, why do I care if we shade on the dice points and then do sampling later? There's a big reason for that. How many people have rendered in mental ray here? A couple. You guys know what happens when you have motion blur or depth of field? What happens to your render times? It's insane. And there's a reason it's insane, is because mental ray, as we'll see later, is a ray tracer. And RenderMan can do ray tracing too. With ray tracing, you need to shoot more rays the more samples you have for depth of field and motion blur, which means you're doing more shading. These are, because they're separate in rays, you only shade once. You just change how much you're collecting the points later. So there's no more shading that happens when you have more depth of field. It does take longer, there's more sampling, but you're not shooting any more rays or reading any more textures or anything like that. So that's a big difference between rays and ray tracing. Motion blur and depth of field are much faster.